Welcome to podcast number 3, where we're going to focus our attention on first order reactions. And what we're going to do then is we're going to look at the different types of calculations that we can do with first order reactions. So what we can find is that the rate expression that we have, and remember that our rate expression is always rate is equal to K times, right? And this is just if we have one reactant here, which is A, but again, it could be K times A to the M times B to the N or whatever it is, right? But this is our rate expression, is we're saying rate is equal to something there. And so we can then integrate this. And depending on if this is first order, 0th order, second order, 15th order, whatever the heck it is, when we integrate it, we're going to get a different value out of it. Well, we can also then rearrange stuff and we can determine something that we call a half-life. All right, a half-life is just how long does it take for half of our material to remain. That's going to be important as we work problems as well. Well, let's take a first order reaction where we have some reactant A producing products. Our rate is going to be equal to K times A to the first power. Well, if we integrate that, what we're going to find is we're going to get the natural log of, okay, A naught divided by A is equal to KT. All right, this is our first time this semester where we're going to see this little naught symbol. All right, that naught symbol is usually going to stand for the original amount of something, or it might stand for standard conditions, depending on our chapter, but we're going to see that a heck of a lot throughout the semester. In this chapter, anytime we see that in any of our different integrated rate law expressions, we're going to think that is the original amount that we started with. The A without that naught symbol is the amount at some time t that we're interested in. All right, so let's see then, we're going to be given these equations on exams, but we've got to be able to use them properly. If we rearrange the equation that we had on the previous slide, and if we're not good at rearranging this yet algebraically, that's okay. We're going to learn how to break up those natural logs and stuff in a little while. Right? But if we rearrange it and move stuff around algebraically, we get that the natural log of A is equal to the natural log of A naught minus KT. And in the general scheme of things, this looks a lot like Y is equal to MX plus B. And if we think back to our previous podcasts, we looked at the relationship between our N2O5, right, our concentration of that, right, and right, how fast our rate of reaction was. Well, notice that when we did that, there was a linear plot. A linear plot came from this equation here, right? Is that the concentration, the amount of that concentration is going to differ at different times. All right, let's calculate then, how would we find the half-life, right, for a reaction here, and this is going to be first order. Okay, remember that that is the amount of time it takes for half of the initial concentration of the reactant to react. And so for the half-life, right, the concentration at some time t is going to be equal to half of the initial concentration. And so if we had our equation like so is equal to KT, what this is saying is that this would be the natural log of, okay, we would have our initial concentration, A naught, divided by, all right, our concentration at the half-life time would be equal to 1/2 of A naught. So those cancel out. So we have the natural log of, all right, the 1/2 in the denominator becomes the natural log of 2 is equal to k times t1/2, which is really, if I rearrange that one more step, this over here. So this is our equation, that the half-life is equal to the natural log of 2 divided by k. And it just so happens that the natural log of 2 is 0.693. So if you don't want to type in the natural log of 2 every time into your calculator, you can just type in 0.693 divided by k to get the half-life. All right, what I want us to get, though, here is that the half-life is independent of our starting concentration. Right, note that A naught is not in this reaction anywhere. That means it's independent of the starting concentration. It means that the half-life is fixed. And so what that means is that it doesn't matter what the starting concentration is for a first-order reaction. Meaning that if I gave you 100 N2O5s, and we found that the half-life of that, when you ended up with 50 of them, it took 1 minute. Okay, if I had 10 N2O5s, if I wanted to find out how long would it take for me to have half as many, 5 of them, it would take the same 1 minute. The half-life is independent of concentration for a first-order reaction. Let's work a sample problem where sucrose hydrolyzes. That just means the fancy word for it breaks apart into the simple sugars glucose and fructose. This happens to be a first-order reaction. We have the half-life for this is 64.2 minutes. How many grams of sucrose in a 1.25 liters of this water solution are hydrolyzed in 1.73 hours? All right. Well, our first step in determining this overall is we're going to figure out the rate constant for this reaction. And for us to find the rate constant for this reaction, right, we need to say that, okay, K is equal to 0.693, or the natural log of 2, divided by our half-life. Okay, well, they gave us the half-life. So this is equal to 0.693 divided by 64.2 minutes. So we end up with 1.08 times 10 to the minus second, and that is in inverse minutes, which are the right units for K. Right? Another way of writing that is this. Remember that K needs to have units of 1 over time for a first-order reaction. All right, so that checks out. Let's continue this problem on the next slide. So, and here we're going to start by determining the concentration right after our 1.73 hours. Okay, well, I want to note that the half-life we used was in minutes. Okay, so this needs to be in minutes as well, right? Those units have to work out. So we have 1.73 hours. There are 60 minutes in an hour. So we have 104 minutes. All right, so I want to know the concentration after 1.73 hours. So we need to use our first order rate law expression that is going to relate our concentrations to our time. So this is going to be the natural log of, all right, our A naught is in the problem as 0.389 molar. Our A is actually what we're looking for in this case. So that's equal to K. K we found on the previous slide by using the half-life. Remember that that was 1.08 times 10 to the minus second. That was per minute. And now our time is 104 minutes. That's why we needed to get that into minutes, is so that those units would cancel each other out properly. So, all right, so there's a lot of algebra here left to do. So let's say we have the natural log of our 0.389 divided by our A is equal to 1.1232. Okay, now to separate these things out, we can take the natural log of the top minus the natural log of what's on the bottom. Those are going to be the same thing, is equal to 1.1232. All right, now I'm going to move my natural log of 0.389 over to the other side. So I have the negative natural log of A is equal to, all right, 1.1232 minus the natural log of 0.389 is going to give us 2.067. All right, so then the natural log of A is equal to minus 2.067. Now to get rid of the natural log, we're going to do e to both sides. So A is equal to e to the negative 2.067, or that A is going to be equal to 0.127 molar. Finally, there. Okay, so there's a lot of algebra that goes into play here, so make sure that you beef up on your algebra skills. If you get lost in that, go back and double check it and see what you can do. All right, finally, we're going to find the mass of our glucose that was hydrolyzed. All right, so the change in concentration was that we started with 0.389 molar, right? We ended up with 0.127. So we changed to 0.262 molar was the change. That was how much is hydrolyzed. So we had 1.25 liters. Oh my goodness, going way up there. We got to go back to that data point. Times 0.262 moles per liter. All right, and then we're going to find this in grams. So 342.35 grams per mole is 112 grams of sucrose hydrolyzed. Woo, there was a lot going on in that problem, right? So these problems do get complex relatively quickly. Our next sample problem entails finding the half-life of nuclear material. All right, so what I want to point out here is that all nuclear material undergoes radioactive decay, right? And we'll talk about nuclear material at the very end of this semester. It's the last chapter that we're going to go over, but all nuclear reactions are first order reactions. And so we can use the exact same equations. Now your textbook might have all these fancy new equations to use for these things. You don't need those. You just need the equations that we already know. So if we want to do, right, the half-life of our nuclear material, it says it undergoes, all right, 8,540 disintegrations per minute initially, but undergoes 6,990 disintegrations per minute after 10 days. What is the half-life? All right, now we could do a whole bunch of stuff, but like these are basically just concentrations. They're just not in moles per liter. So let's just start with our normal thing. Right, we have the natural log of A naught over A is equal to KT. We're going to find K, then get our half-life. So we've got the natural log of 8540 divided by 6990 is equal to K times, all right, well, we have 10 days. Well, if we take the natural log of our 8540 divided by our 6990, we're going to get 0.200 is equal to our K times our 10 days. Dividing both sides by 10, 0.02. All right, and this is per day is equal to K. All right, then we can finally say, okay, the half-life is equal to 0.693 divided by our K. Our half-life is 0.693 divided by 0.02 per day, which is 34.6 days. Right, so they can show you all these fancy new equations, like the natural log of NT over N naught is equal to the negative natural log of 2 times T over T, or sorry, 1/2, and all these different equations and stuff like that. Nah, who cares about that? Just use the equations that we know and trust, and we can get the exact same correct answers. All right, that ends the podcast on first order reactions. Next, we're going to look at zeroth order reactions as a whole themselves.